The final talk of this session, before we move to the spotlights, is from Jessica Bader. Jessica is a PhD researcher focused on controlling text-to-image models at Helmholtz Munich and TUM. Her work has included controlling color and spatial composition, as well as generating out-of-distribution images in flow matching models. And today she will talk about her work on positional control and image generation. Looking forward to that.
Perfect. Hello, everyone. I'm Jessie. And like he said, I'll be talking about positional control in text-to-image. So we're going back into the image space. So you might have noticed that in the last few years, the new text-to-image models have reached this unprecedented level of image quality. So you get really nice images. They're a lot better at the things that used to be very difficult. For example, human faces and hands. They're starting to be able to make words, and they can make images of objects that aren't really naturally seen together. But maybe we're not just interested in our images being pretty, we're also interested in them being exactly what we asked for. And we call this prompt following. And so typically, the way we would measure this is by having a lot of prompts and just kind of see the accuracy on getting these prompts correct. But prompt following, how I've described it, is still kind of broad because it's not exactly the same thing to be able to draw a picture of a person as it is to be able to draw an image of 2 different types of pandas, a snow leopard, a penguin, a wolf, and a bunch of computers. So what we do is we break it up into subtasks. And we have small pools of prompts that we're trying to test and really probe one specific capability. Maybe the most basic capability is single object. But we can also test things like colors and other attributes. We can see how well the model can count. And we can also check if it can put things in the right position. And that's what we're interested in this paper, is looking at if they can put things in the right position. And in the past, this was very difficult. So the results we have here are from GenEval. That's a very standard benchmark for testing the prompt following capabilities of these models. And it has a position task, which is very basic. So you just have 2 objects and 1 2D spatial relationship. So it's just above, below, right, left. And as of 2024, the highest models had 34%. So 1 in 3 is maybe not so ideal. But this changed quite a bit in 2025 when the newer models got a lot better very fast. All of a sudden, everyone can do it quite well, and Blip 3.0 can even get 87%. So it starts to look like maybe this is actually solved. Or maybe it's not. So that's kind of the question that we're looking at in this work, is positional control in text-to-image models solved? Because it looks like the existing benchmarks are starting to saturate. Does this mean that they can actually generalize to more challenging positional prompts? So we introduce a new benchmark, which we call PosEval. It's an extension of the benchmark that I talked about earlier, GenEval. We start by inheriting this position task from GenEval. We call it toObject, and then we extend it up to 3 and 4 objects. We also test some more comprehension prompt comprehension capabilities of the models. So we have these negative prompts where the 2 objects should be not in a certain relation to each other. And then we also have relative prompts, which is things like it should be on the same side or it should be on the opposite side. We also scale up to needing to handle more things at once by having positional attribute binding. In this case, there's 2 objects, 2 attributes. These attributes are always colors, and 1 position. So the model needs to be able to put the pink with the dog, the yellow with the table, and get the position correct. So there's a lot of things going on at the same time. So we'll return to looking at how the models do on this new benchmark. And again, this toObject we saw earlier as position from GenEval. And we see that kind of across the board, the state of the art on these more challenging tasks is a lot lower than it was on this very simple task. What's maybe even more interesting is that Blip 3.0, which had originally done very well, actually doesn't generalize very well to 3 and 4 objects. But on the other hand, FLUX 2, which did a bit worse originally, is now holding a lot more steady as we increase the number of objects. So overall here, I would say there's kind of two takeaways that highlight the need for a benchmark like this. One is that it becomes clear that positional generation is not yet solved. And two, we can also see that the original task that we were evaluating is not actually indicative of whether or not these prompts will generalize, or these models will generalize to more complicated prompts. So now that we have a better way to benchmark and to test the capabilities, we want to look at if we can also improve the capabilities of the models themselves. And because training models is typically very expensive, both in terms of compute and data, it would be really cool if we could do this training free. So the way you typically do this is with what's called layout control. So you end up with this kind of bounding box-based layout where you say exactly where you want each image to end up, and then you try to guide the model to follow this layout. And as it turns out, getting this layout is very easy. You can just hand it to an MLLM. They make it very nicely. But getting the model to follow the layout is a lot more challenging because they're not really trained to take this layout conditioning as a condition. But people figured out how to do it. So at a high level, basically, you can block the cross-attention between certain patches in the image and the parts of the prompt that you don't want to appear in that spot. But everything works. Everything's great. We're all happy. And then we update our architectures. So previously, the results we see on the left are on a UNet-based architecture. And then the field kind of moved to transformer-based architectures. And it turns out that even though it's just an architectural difference, they kind of fundamentally work a little bit different in that the old methods no longer work. So we get these kind of awkward, not really blended images. This is, of course, not ideal. I think I could have made this with a pair of scissors and some glue. So we need something better. We were thinking about it, and what we thought is maybe the reason the models can't blend everything together is because of the strong background information of the color. So basically, in the skateboard, we have a very purple background, and behind the butterfly, there's a lot of green. And maybe if the model can't change the colors in the way it needs to, it won't be able to blend everything together. Actually, this would be a good thing because we don't really care about the backgrounds of these subprompts. We only really cared about the foreground object. So what if we can take our bounding boxes and then extract only the object from it and just combine those? So what does this look like end to end? Well, we start out like all the other models. We take the prompt and we feed it to an MLLM, which will give us a whole bunch of subprompts, each that have one object in them, and a bounding box for where that object should appear in the image. And we're also going to need a background. And then what we're going to do is generate those for S timestamps. And then when we're ready to combine all of them, we're going to use the attention heads to segment the foreground objects. And we will only take the main object, not the background from it, and put them all, kind of compile them all into the background. Then we can just finish the generation for the next steps and kind of trust the model to just make everything look pretty. And it turns out that this time, it can do it. So we're going to go back to our PosEval benchmark, and we're going to compare this with other layout guidance methods. And so our method, which we called Stitch, it can be put onto any transformer-based architecture, and we added on top of 3 of them. And we find that with Qwen-Image, we're able to now create a new state-of-the-art in the accuracy of these models. And on top, the other thing that's nice is that kind of across the board on all the tasks, all the base models, we have double-digit improvements in terms of what the model could do. So it was really able to generalize to these different benchmarks and on different models and on different tasks. But maybe what we're asking now is if the image looks nice, because this kind of glued together image that I showed earlier technically would have passed the accuracy. So maybe we should look at that too. And it turns out, that it does kind of retain the quality that we would have wanted out of the original image. So basically, once we segmented only the foreground object, recompiled everything, now the latent looks in a way that the model is capable of blending everything together and making it look nice. Thank you all for listening. I really appreciate your attention. I guess we can take any questions now.
Exactly. Are there any questions from the audience? Yes, there's 2 questions. Yes, maybe this one first.
Hi, great talk. I'll start with a comment. I love your standard deviations. I hope I can be so blunt, because in benchmark, standard deviations give me much more information than just the expectation. Now the question, if I use this technique for scientific data, I don't know, galaxies, plasma, whatever, turbulences, would I have to resort to a specific model to identify the model in or the object in question? Because in your technique, I understood you segment effectively foreground and background, and then you do things, and you probably resorted to a off-the-shelf model for this. But for me in science, I probably don't have a pre-trained model. So I would have to train that on my own?
Yeah, so it would require starting with a model that can generate the objects that you're interested in. I think that's very fundamentally, yes.
And then we can do one other quick question, and then maybe while we answer that question, everybody who has a spotlight talk afterwards could already position themselves in the first row so that we can switch a bit faster. Yes, and there was yeah, second question was over here.
John, just wanted to make sure that I understood it correctly. So you generate these separate images first, and then you give them as an input so that the final image is created. So that means it only works with edit images.
So it's
image diffusion models.
A little bit different. So we generate them for just some time steps, so it's not a full image yet. And then we extract the partially generated image to combine them and finish. So it does not need to be an editing model because we took it mid-generation.
And how much longer does that take instead of just generating it without your method?
Actually, not a lot. So you have these separate subprompts that for some number of time steps need to be generated separately, but actually that's a very small number. It's like 10 out of 50 typically. On top of it, because typically these objects are not in the same spot as each other, actually we can do it in total that those 10 steps are just twice repeated, not repeated for every single subprompt. And then it's just a small overhead in like putting everything together. It's not like the time steps dominate the process a lot more.
And the bounding boxes work with these noisy images that you have in between?
Yes, so the bounding boxes were how we generated the noisy images. So we generated, for those first time steps, we generated that particular object within the bounding box.
Thank you.
Thank you.
All right, let's thank Jessica again. And